Welcome to the Smithsonian's National Air and Space Museum. My name is Margaret Whitekamp. I'm a curator here in our Space History Department, and I'm delighted to welcome you to our Moving Beyond Earth gallery. This is our gallery, which is dedicated to the Space Shuttle program, the International Space Station, and future human spaceflight. And it's a particularly good setting for our speaker today as a part of our What's New in Aerospace series. And this is a series of lectures and public outreach that we're doing in partnership here at the museum with NASA. And I'm delighted to be able to welcome and thank Mike Green, who helped make this partnership possible. And our speaker today is Dr. Ian Clark, who has a BA, Master's, and PhD from Georgia Tech and works at NASA's Jet Propulsion Laboratory. He is the principal investigator, which means he is the lead scientist and engineer on a project that is called the Low-Density Supersonic Decelerator, which is a way of landing on Mars. And so he's going to talk to us a little bit today about some of the history of landing on Mars and some of his ideas for what is going to come next. So I'm delighted to welcome to the stage Dr. Ian Clark. Thank you.
Thank you. Thank you very much. And thank you very much to the Air and Space Museum for hosting me and allowing me to give this talk at what is really an amazing setting. So I've got a lot of exciting things to talk about today. If we can go ahead and get the presentation up on the screen there. So I'm going to be giving you an overview of how we land on Mars, and then talking about the future of how we're going to be landing on Mars, in particular some of the technologies that they're developing today for the future Mars missions. We call it NASA's Flying Saucer, Learning to Land on Mars. There's a lot more there. And I am the principal investigator on the project. She mentioned I'm one of the scientists. I'm really one of many mad scientists on this project who help come up with some of these ideas and in particular the way to test these technologies. So let's go to the next slide. A few of you hopefully remember that a few years ago we landed the Curiosity rover on the surface of Mars. This is a 1-ton, nuclear-powered, laser-equipped rover that's the size of a small SUV. It is the largest, most massive thing we've ever landed on another planet. And putting it safely on the surface of Mars was a tremendous undertaking of just immense engineering skill, talent, and capability to do that. And one of the reasons why is because of the Mars environment, the Mars atmosphere itself. Mars, of all the planets in the solar system, is probably one of the very toughest to land on. The atmosphere is extremely thin, which means that the ability to generate drag, to slow our vehicle down as it's entering the atmosphere, is mitigated. There's just not much atmosphere to fight against the vehicle to help slow us down. So typically we need very large structures. So the question is, how do we land today? But maybe before we do, one of the neat things about this rover, if we go back one slide, it is on Mars. And in fact, this image that I have on my title slide is from an orbiter around Mars. And the Curiosity rover is right here at the base of Mount Sharp in this image. Let's go 2 slides forward, please. So how did we get Curiosity on the surface of Mars? Let's go ahead and play the video. We start at the top of the atmosphere, and we're going about 10,000 miles an hour. And we have an enormous aeroshell. It's 15 feet in diameter that we use to react against the atmosphere to help slow us down. That takes us from the top of the atmosphere down to an altitude about 6 miles from the surface. And it gets us from 10,000 miles an hour to 1,000 miles an hour. But that's not enough. We have to hit the emergency brake. So we deploy an enormous 60-foot parachute at twice the speed of sound. And that parachute helps us get it from 1,000 miles an hour to 200 miles an hour. But that's still not slow enough. Once we're on the parachute and we're going 200 miles an hour, we deploy the sky crane. The sky crane turns on its rockets and it helps slow us from 200 miles an hour down to just a few miles an hour and get us right above the surface, going very, very slowly. We then lower this enormous rover down towards the ground. It deploys its wheels. We put it safely on the surface. We cut the cables, and the sky crane system flies away and goes off in the distance. And it leaves Curiosity safely on the surface where it is today, doing amazing science for us. That was how we landed Curiosity. Let's go to the next slide. If we look at the technologies that we use to land Curiosity, the big aeroshells, the big supersonic parachutes, and the sky crane system, we can trace a lot of that heritage back to the very first time that we landed something on the surface of Mars, the twin Viking landers in the mid-1970s. the technologies that Viking used are largely the same ones that we use today. There are a couple differences. The aeroshell's changed a little bit. Not the shape of the aeroshell, but how we use the aeroshell. We've learned that we can fly it differently and steer it through the atmosphere to help fly it and steer it to get closer to where we actually want to land. We've gone from uncertainties of 150 miles of where we're going to land on the surface of Mars down to 5 or 6 miles by flying out this aeroshell. We've got new materials on the aeroshell that allow us to see much, much higher heating and enter heavier vehicles because of that. On the landing side, Viking used rockets directly attached to the lander to help safely slow it down and put it on the surface. We've developed airbags that we use to inflate, and then we bounce our rovers on the surface, and we bring them to a slow stop. And of course, we've developed the sky crane system, which gently lowers very large rovers towards the surface. So we've made some improvements on the entry side and on the landing side, but we haven't really made any improvements in 40 years of exploring Mars on the descent side. That is, the supersonic parachute that was used by Viking is still largely the same exact parachute that we use today, just a little bit bigger, as was the case with MSL. So it's an obvious area that as we look to the future and we want to be able to land bigger things on Mars, things that we'd like to be able to improve are on the parachute, our ability to slow down at Mach numbers several times the speed of sound. So let's go to the next slide. Why do we want to do this and what makes it difficult? Well, if we go back to our history of landing rovers on the surface of Mars, we've got a very small Sojourner rover that was part of the Pathfinder mission back in the mid and late 1990s. Then we grew up from the Sojourner rover, which is about this big, to the Mars exploration rovers, the twin rovers, Spirit and Opportunity. We went from a few kilograms to several hundred kilograms for the Mars exploration rovers. Then we landed Phoenix, and most recently we landed Curiosity, which was nearly 1,000 kilograms, 1 metric ton, an enormous rover. As our payloads get bigger and bigger, our vehicles get bigger, but there's a challenge. As the vehicles get bigger, our ability to slow them down is really based on the area. How big is the thing? What's the surface area look like? That's only going up with the square of the diameter. But the volume of that capsule that's using it is going up with a cube diameter. In other words, as we get bigger, we're getting more volume quicker than we're getting surface area. That means we're carrying more mass relative to our ability to slow that mass down. We have more mass, less area. That makes it harder to slow down. It makes it harder as these payloads get bigger and bigger. And they do want to get bigger. You know, the image I have here on the right is, a hypothetical payload of what it would take to put humans on the surface of Mars. Let's go to the next slide. And so if we look at the future of missions that we want to put on the surface of Mars, we see things like rockets, maybe that we want to use to return samples from the surface of Mars. We think about maybe putting greenhouses down to see if we could put and grow plants on the surface of Mars, things that would be necessary to survive. Maybe we want to put payloads down that see if we can take the carbon dioxide atmosphere and create rocket fuel from it. And eventually, as we cast our eyes to the horizon, we want to be able to put humans safely on the surface of Mars. And that means all of the stuff that has to accommodate humans, all of the tools, all of the food, water, resources, all of the iPads, iPhones, whatever the astronauts need to survive on the surface of Mars for days, weeks, or months at a time. It's an enormous amount of stuff that has to get put down, and it's several times larger than anything we've ever been able to safely land on the surface of Mars to date. Let's go to the next slide, please. So we are at the National Air and Space Museum, which is the best museum in the world, which means I have to talk a little bit about history. This problem of landing large things on Mars isn't new. In fact, it's one very similar that we had about in the early 1960s. One of the very first concepts for a Mars mission was called the Mars Voyager project. It's not the Voyager that we later would send to the outer planets. This was a predecessor. And the idea was that we wanted to use the Saturn V, the rocket that we used to send humans to the moon. We wanted to take that enormous rocket and all of the capability it had to send payloads into space and use it to send a payload to Mars. This was in the early 1960s. We actually knew very little about the Martian atmosphere at the time. We had a couple of spacecraft that had done flybys and gotten some soundings of the atmosphere, but we really didn't have a great idea. Initially, we did know that it was thinner than the Earth's atmosphere, that it was going to be challenging, but we didn't know how much thinner. We thought, it might have been 10% the thickness of Earth's atmosphere. And then later on, we started getting better data, and we realized it's not 10%, it's not 8%, it's not 6, 5, 4. Eventually, by the mid and late 1960s, we realized that the thickness of the Martian atmosphere was less than 1% the thickness of Earth's atmosphere. That means it's going to be very, very difficult to slow down the payload big enough to fit into this large Saturn V rocket. And so in that that problem, that quandary, we started developing new ideas of slowing our rockets and our entry vehicles down. Let's go to the next slide. For the first time, and you can go ahead and play the video on the top right, for the first time we started taking parachutes, things that we've used at low altitudes and relatively low speeds, and trying to deploy them at several times the speed of sound to see how they behave. Will they successfully inflate? What do they look like when they inflate? How much drag do you get out of them? Does the material survive? Can you make them light enough to be used on a Mars mission? We also tried a number of other devices, more innovative devices. We thought about taking inflatable structures and attaching them directly to the aeroshell, the entry vehicle itself. And then we would inflate these as we're entering the Martian atmosphere, grow the size of the aeroshell, create more drag that way, and allow us to slow down easier. There was lots of testing that went on to support these ideas. Lots of parachute testing at high altitudes and very, very fast speeds, several times the speed of sound. Lots of wind tunnel testing of devices like you see there in the middle. That's several stills from a deployment video at several times the speed of sound, about 4.4 times the speed of sound of an article about 5 feet high or so. We even developed articles that were in the 20 to 30 foot size, and we would drop them from a helicopter and see how they inflate and see how they perform. And then we would continue to test them using large aeroshells that looked very similar to the aeroshells that we would use to land the Viking landers on the surface of Mars. Eventually, the Mars Voyager program would go away. It was a little too ambitious for the time, and it would be down-selected in favor of the Mars Viking project. The Mars Viking project was a smaller payload. We understood the Martian atmosphere a little bit better at that time, and eventually the work in these attached decelerators, or what we refer to as supersonic inflatable aerodynamic decelerators, we love our acronyms, so we call them SIADs, would go away in favor of a parachute. Viking would only really need a supersonic parachute to proceed. Let's go to the next slide. So here we are today, facing the same problem that the Mars Voyager program faced, and looking at the same solutions that they were considering, namely large inflatable structures that we can deploy at several times the speed of sound to help us slow down these enormous payloads as they enter the very, very thin, very tenuous Martian atmosphere. We have inflatable structures that look like giant inflatable donuts that we can inflate at 4 times the speed of sound and go from 15 feet to 20 feet or 22 feet in diameter. We have another device I'll talk about that goes even larger, almost 30 feet in diameter. And we have a new supersonic parachute that we're developing, something much, much bigger than any parachute we've ever tested before at these speeds. It's about 100 feet in diameter, the size of a small warehouse when it's inflated. And we're going to be testing it at over 2.5 times the speed of sound. So let's go to the next slide. A little bit of detail. There's a lot of words with a lot of syllables on here. The real basic idea with this first one, we call this the 6-meter torus. It's a giant inflated donut. And again, we use it, we inflate it very quickly, and we grow the size of the vehicle to create bigger surface area to react against the atmosphere, create more drag, and help us slow down. It's designed to be pressurized using not a lot of pressure, a few pounds per square inch, but otherwise create a rigid structure. And why do we like rigid structures? Well, aerodynamicists have a few tricks up their sleeves. And one of our favorite is that we like to be able to test very small things in wind tunnels or in with ballistic ranges. We take very small models and we shoot them out of a cannon. And we watch how they behave, how they fly, how they move. And we're able to back out the aerodynamics of the vehicle that way. And we feel comfortable that testing these very small articles, that we can grow those results to very, very large articles. So when we test 6-inch diameter wind tunnel models, that the results that we see of the aerodynamics are scalable to these 15-foot diameter vehicles. It also means that we understand the geometry. When we inflate it, we know what the shape of the device looks like. So when we first started developing these inflatable devices, we wanted something that we could make rigid, that we'd have that determinism, and that would help simplify what the testing was going to look like to convince ourselves this would work at Mars. Let's go to the next slide. But we can't do that forever. We really wanted to have a rigid device, but at some point these devices grow so large you just cannot make them rigid anymore, and they will have some flexibility associated with it. And so we realized that, and we realized that now is the time to start testing and understand what that flexibility means. So we developed another device that we're going to be testing. It's even larger than the inflated torus. It's called an attached isotensinoid, and it looks very similar to devices that were tested in the 1960s. We've taken a lot of that knowledge, a lot of that experience, and now we're growing these devices, and we're going to be testing them at scales more relevant to what they would need to be used at Mars. So we've got a device that rather than we inflate to several psi, it's predominantly ram air inflated. That is, we have scoops on the side of it that help swallow and ingest the oncoming air and pressurize it that way. It's an enormous device, but it also has a lot of flexibility associated with it. So we'll get to see, okay, if this device isn't rigid and it is flexible, what does that flexibility mean? How does it interact with the rigid vehicle in front of it? Can we inflate it in the right way? Does it inflate symmetrically? Does it inflate in a controlled way? And does it, once it's inflated, does it achieve a nice, good geometry that helps produce lots of drag for us to slow down? Let's go to the next slide. So the third device is the large supersonic parachute. And I say large, it is 100 feet in diameter. It's more than 2.5 times the area of any parachute we've ever used in the past at supersonic speeds. And it's very similar, the parachute we're using is very similar to a parachute we've got experience with. It's a ring sail parachute. It's the same kind of basic parachute used by the Apollo, Gemini, Mercury programs, and more recently by the Orion programs. So you see a little bit of the scale. This is the Phoenix lander that we landed on Mars a few years ago, the Viking lander parachute from the 1970s, the MSL parachute, and here we see the parachute that the Low-Density Supersonic Decelerator project is developing, or LDSD parachute. And it's the size of a very enormous jet, a 747. Let's go to the next slide. So we've got these devices, but in order to make sure that they work, and we need to test them here at Earth, make sure that we understand how they perform, how they behave. We want to test them here before they have to work at Mars. And one of the hardest things about the LDSD project is figuring out how to test these devices. And the reason is we came up with a test method, a way of decomposing all of the different aspects of these devices, and we started looking around the world for where we could test to achieve the knowledge necessary for each of these different phases. We looked at wind tunnels, we looked at all these different tests architectures that existed, and we realized that for the size of the devices that we're developing and the conditions that we needed to test them in, there were no places in the world able to test them. And that's you kind of have to pause for a moment and think about what that means. We've been exploring space for 60 years. We've built monuments to our endeavors, right? We've got wind tunnels that are the size of entire city blocks and that use more power than 3 nuclear aircraft carriers. We've got vacuum chambers that are just as large. We've got test stands, thrust structures that are as big as buildings, and we built buildings that at the time were the largest in the world. All of that infrastructure that we've used for decades of space exploration, we are now beginning to outgrow. And when it comes to devices like this, that have to be the scale that they are and get tested at the conditions that we need to test them, there was nowhere in the world that we could do it. So we had to develop new ways of testing them. So let's go to the next. The first of those, for that attached torus, that inflatable drag device, the device that we refer to as the SIAD, we want to expose it to aerodynamic loading similar to what it would see at Mars. We want to put it exposed to wind and make sure that it's structurally strong enough to survive the aerodynamic loads that it's going to see at Mars. So we went out to the desert. We went to the China Lake Naval Air Weapons Station where they have a standard gauge railroad track that's about 5 miles long. We built a 20-foot tall, 40-ton welded steel siege tower that we put on this standard gauge railroad track. We put a aeroshell simulator, and then we packed the SIAD around the periphery. On the back end of this are 6 solid rocket motors. These are Nike solid rocket motors that were originally cast and built in the 1950s and would have been sent around cities like Los Angeles to protect us from Soviet bombers. But we've got a lot of these surplus rockets left over. So we took 6 of them and we put them on another sled, a pusher sled. So let's play a video. Go ahead. We light those rockets, the 6 rockets ignite, and they take the sled, this 40-ton sled, from 0 to 300 miles an hour in about 2 seconds. Once we get going at several hundred miles an hour, we now have aerodynamic loads that we can test the SIAD. So we inflate the SIAD. We deploy it from this mock aeroshell. We see how it inflates. We put the air into it. We see how it emerges from a very stowed configuration. Here you have a high-speed video in slow motion. And once it's inflated, we see, is it strong enough? Does it survive? Does it develop holes? Does the fabric hold? Does the shape hold? Is the shape what we expected it to be when it's exposed to these very high loads? Now, we're going very fast, several hundred miles an hour, but it's actually significantly slower than we would be going at Mars. And that's because one of the characteristics that you want to test at is the dynamic pressure. It's the product of the density and the square velocity. So the density here at the surface of Earth is much, much higher than it is at Mars. We don't have to be going as fast to achieve the same aerodynamic loads. So we do these tests, we see that the devices survive, and they survive the structural loads necessary to work at Mars. Next slide, please. We also want to test the parachute. And even before we selected the parachute we wanted to develop, keeping in mind that the parachute we were testing, that we are developing, could be the parachute that's used for the next several decades of Mars exploration, we wanted to figure out what that parachute should look like. So we went into the world's biggest wind tunnel, the 80 by 120 at NASA Ames outside San Francisco. And we tested over 50 different parachutes. And the way that we tested them is we started with one parachute. We flew it. We saw how it behaved. We saw how much drag it generated. We tried measuring some of the aerodynamics. We put little smoke bombs up at the front, and we'd see the smoke and see how the smoke flowed around the parachute. We do little streams of smoke and see what the flow field, the aerodynamics looked like around the parachute. And then once we got some data, we turn off the wind, and we go and we cut some holes in it. And we'd say, all right, let's try some holes over here and fly the parachute. Now let's try some holes over here and fly the parachute. And we did that to help optimize the drag of the parachute, but also another characteristic of parachute, stability. There's usually a race condition. The two things are competing. The more drag it generates, the less stable, the more the parachute wants to move around and fly all over the place. But you can put holes in it, decrease the amount of drag it generates, and create a more stable parachute. So you wanted to try to find what the best mix of those two parameters were. So we went into this giant wind tunnel to do that. That's what helps us pick a parachute configuration. Next slide. But we also needed to test the strength of the parachute to make sure it was strong enough. For that, we came up with another idea based on rocket sled. We went out to that same desert railroad track, and we built an enormous structure. This is a giant tripod that's in the desert above the railroad track. And here, you can't really see, but there's a few people down in the lower to give you a sense of scale. You also see that there's this long sled here and some much larger rocket motors. So let's go to the next slide and play the video, and I'll talk you through how this works. We start with a helicopter, a Navy Seahawk or a Black Hawk helicopter. The helicopter flies down, picks up our parachute, our tightly packed parachute, and carries it to an altitude of about 4,000 feet. From that altitude, the parachute is released, begins inflating very slowly, and attached to the bottom of this parachute is a rope, a 4,000-foot long rope that goes all the way down to the ground, wraps itself around a pulley, and then we tie it off to the back of a rocket sled. As that rope comes down, it latches up to the rocket sled. We light the rockets. The rockets take off horizontally, and they pull on that rope, and they pull on the parachute, and they generate over 100,000 pounds of force. It's an enormous amount of force, but it's an amount of force that, again, these parachutes are going to have to be able to survive if they're going to be used at Mars, and if they're going to work at Mars. So the test is over. The parachute gently descends to the desert floor. We see that the parachute had a failure. We go and we pick the parachute off the desert floor. We brush the sagebrush out, pull the sand out, and then we celebrate. And we try to high five a little bit. Engineers, calculus, rockets, good. High fiving, not so good at. So those were just structural tests. That was just to make sure that things survive the loads necessary. We also need to see how these devices fly, how they deploy, how they inflate, and we need to do that in conditions similar to what they'd see at Mars. That means going several times the speed of sound and doing it in a very, very thin atmosphere. And there is a place here on Earth to do that. You just have to go very, very high in the sky to do that, almost halfway to the edge of space, in fact. So let's go to the next slide. So we built a test vehicle. We took a 15-foot diameter aeroshell, very similar looking to the one that we used to land Curiosity on the surface of Mars, and we put our technologies on it. And we loaded it with all kinds of instrumentation, load cells, pressure transducers, thermocouples, all sorts of cameras, high speed, high definition, high resolution, all that kind of stuff. And then we shipped it out to Hawaii, to the west coast of Kauai. Let's go to the next slide. I'll talk through this. Next slide. And we attached it to a balloon, a giant balloon. There's a tether here that goes up around this launch tower, and then there's more tethers, and then a balloon that's laid out many, many hundreds of feet back behind here. So we use this balloon. Let's go to the next slide. And play the video, please. We start very early in the morning, actually about 11 p.m. the night before, to attach our test vehicle to this balloon. We hoist it up on the tower, and then we begin inflating this balloon. And I say it's an enormous balloon. It's 34 million cubic feet in volume. That's maybe hard to fathom, but think about a large football stadium. where are we, Washington, so the Redskins game. Next time you're at a Redskins game, sitting in that stadium, think about a balloon that at altitude is as large as that entire stadium. And that's the balloon that we used. Several thousand pounds of helium, and the balloon itself weighed several thousand pounds, even though it's made from a very thin material, like a saran wrap or a very thin garbage bag. And we needed a balloon that big to hoist our test vehicle because our test vehicle weighs 7,000 pounds, and we want to get it very, very high in the sky. So here it is at altitude. In fact, the test vehicle is a few little pixels down at the bottom of that image.
Attention all stations. Attention
and then we got
all
ready to
stations.
test.
Test vehicle is go for drop. I repeat, test vehicle is go for drop. 4, 3, 2, 1, drop.
So the balloon carries us to an altitude of 120,000 feet. Then we released our test vehicle from the balloon. We spin it up for stability, and then we light a giant solid rocket motor. A solid rocket motor that's more typically used as the third stage of a launch vehicle or to send spacecraft from Earth orbit all the way to Mars. But this giant rocket motor takes our enormous 15-foot test vehicle from an altitude of 120,000 feet to an altitude of 180,000 feet. And it gets moving very, very fast. In fact, over 4 times the speed of sound. You see the balloon in the background. The balloon got very high. We put a tear in it. It begins coming back. It crashes into the Pacific Ocean. We go and we collect the balloon and all the debris. We want to be good stewards of the environment. You know, please don't litter. But meanwhile, the spacecraft is flying through the atmosphere. When that motor burns out, after about 70 seconds, we're going almost 3,000 miles an hour, and we're now at an altitude an Earth's atmosphere that's very similar to the atmosphere density that we would see if we were to use these devices at Mars. So we despin the vehicle, we deploy camera lens covers that are protecting our cameras, and then we inflate our device. In a fraction of a second, we go from a tightly packed, tightly stowed configuration to something that's now 20 feet in diameter, and again, going 3,000 miles an hour. We see how the device behaves, we see how rigid it is, we see the shape it takes, we see that it performs and survives all of the aerodynamic loads. And then we get ready to test our parachute. At 2,000 miles an hour, we shoot a 40-pound pack off the back of the vehicle, 200 feet per second, which inflates another drag device, a balloon parachute. Looks like a giant supersonic acorn, you know, something that Scrat would chase after in the Ice Age movies. This inflates, and it begins pulling our parachute off the back of the vehicle. And we try to inflate 200 pounds of nylon and Kevlar in a 2,000 mile an hour wind and see what happens. And we learn from that. Meanwhile, the vehicle decelerates. That little bit of pressure that we put into our inflated device is not enough. As the device gets lower and lower in the Earth's altitude, the atmospheric pressure begins building up and collapsing it. So it begins deflating and flopping around a little bit, but that's all expected. And then all of this lands in the Pacific Ocean. You see an image of the parachute that's just underneath the water there. And another image of it. Looks like a giant jellyfish. And we had some help. The Navy Explosive Ordnance Disposal Team went to help them recover this test vehicle. In fact, these are 2 gentlemen sitting on it, on our test vehicle as they're waiting for the recovery boat to come. And they're wearing cameras. At one point, the gentleman turns to the other and says, "Bro, there's nobody else in the world I'd rather be sitting on a sinking spaceship in the middle of the Pacific Ocean with than you." And they do a fist bump, and they high five. And then they help us pull the vehicle out of the water. And they help us pull the parachute out of the water. And we take this vehicle, we take the technologies, we take the inflatable device, the parachute, we take all the cameras, all the data we get, and we start to understand what happened in that flight. So let's go to the next slide. And we had a number of tremendous accomplishments. For this test, really, this test that we conducted last June was really just a shakeout test. Nobody had done anything like this in over 40 years. We developed a new vehicle, a new balloon capability, an entirely new test architecture, and we just wanted to see, does it work? Will it help us get to the conditions necessary to test the technologies that we're developing? We got lucky because the technologies were actually ready a year ahead of schedule, and we got to put them on this vehicle and see how they performed a year ahead of schedule. And we had some tremendous accomplishments. We inflated the largest inflatable device ever deployed at supersonic conditions. We deployed the largest balloon, that giant supersonic acorn that's in the lower right corner there. Largest balloon ever inflated at several times the speed of sound. We performed the first ever pilot deployment, that is using one device to help deploy the other, pilot deployment of a supersonic parachute. We deployed the largest supersonic parachute ever. We got to see how it began to inflate, what it looked like when it began to inflate, and how it behaved during the inflation process. And the quantity and the quality of the data that we got was orders of magnitude above and beyond anything that we've ever had before in 4 decades of exploring Mars. So let's go to the next slide. But that was just a start. We've got 2 more tests coming up in 2015, and we're presently building 2 more test vehicles. This is in the high bay at JPL. And it's the data from those tests, it's the technologies that we're testing that are going to be used to explore and develop and design and land safely the future explorers of Mars. That means the payloads, the more capable, more exciting, more massive rovers that we're going to put on the surface of Mars, and the payloads that will precede humans, and eventually, hopefully, one day to be used to land humans on the surface of Mars. So I've got one more slide, and it's a quote. It's actually a quote from Teddy Roosevelt that I think is very applicable, particularly when it comes to technology development, but also more broadly applicable to space exploration in general. And the quote is, "It is far better it is to dare mighty things, to win glorious triumphs, even though checkered by failure, than to rank with those timid spirits who neither enjoy nor suffer much, because they live in the gray twilight that knows neither victory nor defeat." We got to see a lot of success, and we also got to see a parachute not work the way that we wanted to, but it's lessons learned, it's data that we can then go and use to design the next generation of parachute that we're getting ready to test again in 2015. So with that, I'm done, and I'll take any questions if you guys want to play a round of Stump the PI.
Dr. Clark, thank you very much. We are very excited to have the chance to ask you some questions about the presentation. I know I learned a ton, and I'm really interested in this. If anyone would like to ask a question of Dr. Ian Clark, you can come over to me, and we're going to ask you to tell us your first name and where you're from, and then ask your question.
Hi, my name is Brianna, and I'm from Washington, D.C. My school is Blow Pierce. I have a question about the human, about landing on Mars. Mm-hmm. So when you said you were planting food and materials that we need, do you want to plant trees? Because trees are the actual the oxygen on Earth. So you're going to plant trees on Mars?
That's certainly one of the possibilities. You know, really, the things I work on and how do you land those payloads safely on the surface of Mars? Other folks are working on what those payloads will need to be for humans to live on the surface of Mars. So, you know, do we bring our own plants? Do we bring what kind of plants do they need, you know, to survive, to generate the food? And maybe they do use trees. It's hard to say.
Hello, my name is Deshayla Bailey, and I'm from Washington, D.C., and my school is Blow Pierce. And I want to ask you, was it hard making the inflatable balloon?
Was it hard making the balloon?
Mm-hmm.
I didn't make the balloon myself, but I suspect it was. I mean, the balloon it's enormous. It's so much material that they've got to work with, and you have to, very, very thin material. Just a little bit of tear in this very thin material, and the balloon won't inflate. And it will deflate, and you won't be able to do your mission. And then it has to survive. It has to carry this enormously heavy vehicle up to extremely high altitudes. So, though I don't know for sure, I suspect it was very difficult to build the balloon.
Thank you very much. Do I have our next question ready? Okay. Come on up. Can you tell us your name and then where you're from and ask your question? Put the mic right up to your mouth.
My name is Julie Rodriguez, and I'm from Washington, D.C., and my school is Blow Pierce. And my question is about NASA thinking of making possible for humans to live on Mars. And I was asking do you know how to bring the soil that you need to plant plants on Mars?
How do we bring the soil that we need to plant plants on Mars? That's an excellent question. So I was joking mostly when I said stump the PI. But you guys are doing a very good job. Anybody want Star Wars trivia? Or no? How do you bring the soil? Well, you know, first you have to figure out what that soil looks like. Maybe, you know, we know what the soil here at Earth looks like, and we know how well plants grow in that. But maybe a good question is, can we use the material, the dirt that is there on Mars now to grow plants? I don't know the answer to that, and I'm not sure if others know the answer to that, but that might be something that we want to look at. There might be plants that work very well here on Earth that also work at Mars in a controlled environment. That is, maybe we build a capsule around them and we put a different environment, not using just the carbon dioxide of the Martian atmosphere, but maybe we bring some of our own gases to put in there to help the plants grow, but otherwise using the Martian soil. There's lots of ideas out there, and I think people are, that's one of the questions that people are trying to answer today as we prepare for eventually putting humans on the surface of Mars. Thank you.
Thank you. Can you move right up, please? Tell us your name and where you're from.
My name is Taylor, and I'm from Washington, D.C., and my school is Blue Pierce. I wanted to know how you're going to build the parachute for 2015.
How did we build the parachute for 2015? Oh, how are we going to build the parachute? Much stronger than the one that we previously built. A parachute is really made from lightweight materials. I say lightweight, it's nylon, like what your camping tent might be made out of. It's predominantly nylon, but we add much stronger materials like Kevlar, which is what's used for bulletproof vests. And what we can do is change where we use the Kevlar relative to where we use the nylon and help the parachute carry loads better, carry stresses better in that geometry. So that's one of the key things that we're doing. We're changing the basic configuration to add more skeletal Kevlar, more structure that can help carry some of the higher loads that it sees during inflation. Great question. I knew the answer.
I'm going to interject one question. I was struck as I was watching this that it's a tremendous amount of engineering and scientific knowledge, but also looks like an awful lot of fun. I mean, giant rocket sleds. How did you get interested in this as a kid? Was this an interest that you had as a child?
Oh, absolutely. I'd always been interested in space as a kid. And I think one of the earliest things was just Legos, playing around with Legos and building things that way. In fact, it wasn't until my senior year in high school that I understood that there was such a thing as aerospace engineering. I thought I was going to go into astronomy to, study planets, and that's the path. And then a friend of mine who was applying to schools said he was applying in aerospace engineering. I was like, what? There's I can build things and it can be in aerospace. So that's what I ended up getting into. Eventually found my path, towards doing stuff like this, which, as you point out, is a tremendous amount of fun.
Can you step up to tell us your name, where you're from, and your question? Right up. Okay.
My name is Sequan Faulkner. I'm from Washington, D.C. My school is Blow Pierce. My question is, will you ever do tests on different planets?
Will we ever test on other planets?
Yes.
We like to test here on Earth because generally we can control those tests a little bit better. It's a little easier to test here on Earth. And as much as we can replicate the environments and the conditions that are necessary to survive going to other planets, we'll continue to test here on Earth. That doesn't mean we won't. There might be things that, we just can't convince ourselves that we can do a test well enough here on Earth. We are going to have to send it to another planet. We haven't had to do that yet, but it's certainly a possibility.
Hello, my name is Micaiah Wooten, and I'm from D.C., and my school is Blow Pierce. And my question is about how much would it cost for all those test flights and launches?
How much does it cost? The entire cost from the beginning to the end of the Low-Density Supersonic Decelerator project is a little less than $200 million. It's a lot.
Very good value for the money.
Oh, it's absolutely good value. The missions that we used, the Curiosity mission was more than $1 billion, right? So we're developing the technologies that will allow these very large, very capable, very exciting science missions to safely land on the surface. And we're doing it at a very small fraction of the overall cost of those missions.
Hi, I'm Daniel Davey. I'm from Austin, Texas, but I'm currently pursuing a PhD in physics at William & Mary. So actually, our projects are a little bit more expensive.
Yeah.
The LHC was like $12 billion. But I was wondering, what exactly caused the failure in the parachute? What happened with that? I mean, we saw it, but you didn't. I was wondering, what were the details there?
Okay. Basically, the parachute shape itself was something that we had come up with out of that earlier wind tunnel testing. And the way that we test is we generally have them fully inflated and we watch how they fly. What we saw was that when the parachute began inflating, that shape that we had was just not a very good shape for surviving the stresses and the loads that it sees during the inflation process. Parachutes typically are very curved, or certainly they have a lot of curvature when they're inflated. What we started with was a combination of a geometry that starts very curved, but otherwise has a very flat top. A parachute at its core is a pressure vessel. It holds a lot of pressure and helps generate drag. The stresses in a pressure vessel are a function of how much pressure is inside of it and the curvature, the local radius of curvature of the parachute. And what we saw was, even though there wasn't a lot of pressure in it, with that very flat top, you could develop very, very high stresses very early on. And it's a shape that you don't have and when it's fully inflated, but that you can get when it's inflating. And that's what damaged the parachute.
Sorry. So what are you, do you guys have a solution to fix it, or what's the...
Put more curvature back in, for one.
Well, yeah.
So we're going to remove the flat top, make it more hemispherical, or at least what's called a quarter sphere, and add more Kevlar, more skeletal structure that can help take and reduce some of the stresses on the fabric in that region. The design that we're going to, if you have a little bit of tear in the fabric, it ends up being very localized. The Kevlar will stop that tear from propagating to the rest of the parachute, or at least that's the idea, and that's what we have to go and test and hopefully find out is true.
I'm David Kneproth from Portland, Oregon. I was wondering, besides Mars, are there any locations that there are plans to deliver a payload to? And if not, what would you think would be the most interesting place besides Mars to deliver a payload?
Besides Mars, yeah. I mean, we've got spacecraft that are going all over the solar system. And my personal, where I would like to see a payload next, I mean, there's a lot of exciting moons of Jupiter and of Saturn that I think would be, just fascinating places to explore. Maybe of all of them, Europa, having a payload land on the surface of Europa, where they have a very thick layer of ice on it, and maybe even dive into the ice a little bit, where scientists hypothesize that there's a subsurface ocean underneath. I think that would be something very fascinating and exciting to explore.
So I understand that you've been doing this test that and testing the structure, and will the structure work? Can it stand up under the supersonic forces? The question of does it work is, can you maintain the integrity of the structure? Will the parachute work? The other question that strikes me is, does it work? Does it decelerate? If you inflate this thing at supersonic speeds, does it get slower?
Well, so does it work? Can you inflate it? Will it survive the inflation? And then once it's inflated, does it do the job that it needs to? It will decelerate, but does it decelerate enough? Does it generate all of the drag that you need? Right? Does it generate enough force to help slow you down in time? Right? Because a Mars entry is a very, very fast process. We refer to the Curiosity landing as 7 minutes of terror, because it takes 7 minutes to go from the top of the atmosphere down to the surface. And the first 2 or 3 of that is taking us from almost 70 miles above the surface down to the final 6 miles above the surface. We do that part very quickly, then we hit the emergency brake, deploy the parachute, and we spend the other several minutes helping slow us down and get us safely on the surface. So that's one of the things that we're testing to find out. And that's why we have to do tests like the high altitude test, because that performance is something that's very much a function of the environment in which you're using these devices. I say environment, the density of the atmosphere and the speed at which it's going in particular. So those are all things that we test, yep.
Very good, thank you.
My name is Mark Bremer. I'm from Columbia, South Carolina. Yeah, actually, one question. When you deploy the balloons, can you do like a non-linear trajectory? Are you actually be thinking about steering the vehicle to do a series of S turns?
So
when you come in, it gives you a lot more atmosphere. So like the shuttle, the shuttle does when it comes in. I actually saw a simulation in a thin atmosphere of that.
So lots of good questions in there. A little bit long of an answer. First, hail to Columbia. I actually went to high school at Irmo, which is right outside Columbia. do we steer the vehicle? Well, for this test flight, no, we didn't steer the vehicle. It was a passive vehicle that we just wanted to get up to the conditions that we would be using the inflatable devices and the parachute. We did steer the vehicle for the Curiosity lander. One of the nice tricks that you can play with a vehicle, and that we learned even going back to Viking, is that even though it's a very blunt shaped geometry with the drag characteristics and stability characteristics of a barn door, you can fly it at an angle. And in doing so, it actually generates a little bit of lift. Not as much lift as, say, an airplane, and nothing close to that. But even a little bit of lift helps a lot when you're entering in the Martian atmosphere. We can use that lift to fly higher in the Martian atmosphere and spend longer flying higher. We don't come straight in. We come flying and we try to coast a little bit. We also steer it. We do bank it a little bit to try to give more time decelerating. But, you don't have a whole lot of atmosphere to do that in. And particularly at higher altitudes at Mars, the atmosphere is very thin. So we do it a little bit lower, but it is one of the tricks that we play to help slow down.
Well, thank you very much, Dr. Ian Clark. It has been really a pleasure to hear from you this afternoon. I want to make our visitors here and on NASA TV aware. In 2012, Dr. Clark was awarded an Presidential Early Career in Science and Engineering Award, and we can see from his presentation today why the President himself would have given him one of the highest science and engineering awards in this country. We're delighted to have had you here as a part of the What's New in Aerospace program here at the National Air and Space Museum. We're doing this in partnership with NASA and thanks to some funding from Boeing. And we look forward next year to both your successful tests, and we will be developing the new Boeing Milestones of Flight gallery. So you'll be able to see that here back at the museum. So thank you for your presence here. Thank you to the school children who joined us, and thank you to those on NASA TV.
Thank you very much for having me.